Jyoti, today we are going to talk about antenna measurements. And again, I will give the outline of presentation will be that we will be talking about system parameters, what motivates us to measure, to carry out extensive and accurate and precise measurements. Then few measurement techniques which I try to see whether I can cover, but I will put more emphasis on antenna measurement. Here I have listed passive intermodulation. Although you must have heard intermod products in the amplifiers and all that, but passive intermodulation also is there in the part of antenna measurement which we have to carry out in our spacecraft or even in ground segments antennas. And then measurement techniques for both amplitude and phase, radiation characteristics of antenna, then PIM measurements. Then the very important is G by T. You must have heard in your the figure of merit, which we generally call for the performance of a antenna system. Now why we do the measurement, we have to be very accurate, is because we want to validate our CAD design. We want to validate our analytical tools. We have to go for a cost-effective solution. And we have to go for simulation of performance in different environment, because you need to, once the type of environment in which the antenna is going to be placed, that simulation of the performance in those environment we have to carry out the measurements. And the measurement becomes very, very important in terms of the coexistence of multi-band, multi-user and different services which are available in the space and communication segments. Currently we are having 11 operational satellites. They all are working from UHF to Ka band, and these bands are all you are seeing at certain locations like 74. If you see here, this place, this is 74 degree east on the longitude on this geostationary orbit. How many satellites? 1, 2, 3, 4, 5. 4 satellites are there. So all have to coexist together, and they are all having multi-band systems. So they have to see in the individual performance of each satellite very accurately, so that we should be able to predict what is happening, if in any case of eventuality. So then this is just to give you in the transporter growth from the 2008 to 2012 is going to be nearly twofold, and the services are in different frequency bands. And this is what I introduced you yesterday, all different types of antenna systems which are going to be used for spacecraft, whether it is reflector antennas or array antennas or passive components for different requirements. Then large or earth stations antennas, medium size earth station antennas, small size handheld terminals, and today we are talking about your BSNL and all this community, even for your users, they are using the Kodak or the rural techniques for their for the telephone connection in the countryside. Even they had the requirement of very large. So depending upon what type of antenna we are talking about, whether it is for mass production or it is for whenever the mass production comes, the cost has to be very very effective, and the production, the sensitivity analysis for the antenna designer has to be, he has to carry out and see that even with the production tools which are used for the development of this antenna, they should be cost effective. There should not be any deviation in the performance when we are using the commercial tools. And there, just to give you a glimpse of, yesterday I was showing you some of the components. The one component is having one single coupler, as you see in the here, is having a lot of components in itself, and the characterization and the performance measurement of each and every individual component becomes very important. Because even if you are having a two component simple waveguides and the return loss of each or your impedance both are matching to each other, they are matched to each waveguide impedance is matched, and you see the VSLR or your return loss, and you individual performance, and when you cascade, you never get the same behavior. So you have to, and that is not possible also. So you have to know when you integrate n number of components, what is going to be the predicted performance of the cascaded performance of the total assembly. So that's the reason we need to evaluate the performance of each and every component. And then when we are working on the different antennas are there mounted on a spacecraft, we have to see whether there is no mutual coupling should be there. Even if there is a mutual coupling, the interference should not affect the main features of the performance of. So we have to evaluate the performance. There is nothing more. You can get a software, you can get design tools to design your antenna components, and when you want to do the simulation to see how their interference are there, then that really measurement only helps you. No, nothing, you cannot get a tool and predict the performance of the in space, in orbit performance when they are in an environment in which they are maybe some 4 or 5 reflectors of different frequency bands are there, the effect of each other will be there. Now I tell you one very phenomena which we saw, that when EMI EMC problems come sometime in the satellite systems also. The moment you make the transmitter on, so telemetry or telecommand signals which are very having very weak signals, and the strength of the signals is very small, even the side lobe of the order of 20 or 30 dB may get the interference to the system which is already placed in the same cuboid structure which you are seeing here. So the evaluation of all the systems working together is very important, and that cannot be done on any analytical tool. You cannot carry out anything. So you have to go for simulations. And how to do that simulation in space? Before launching in the space, we have to carry out all this measurement in the ground. Now, the parameters which I will be touching upon is the antenna parameters, the impedance matching and inertial loss, power handling capability, the group delay, the noise, G by T, ERP. I will be able to touch, I think, antenna parameters and PIM and G by T. Now, if you talk about antenna parameters, then the gain, radiation pattern, repolarization, cross polarization, VSLR and insertion loss are the most important parameters. Now, for any antenna which is having depending upon its type of antenna which is there, like whether it's a planar antenna or a reflector antenna, the measurement techniques is selected according to the type of antenna also. Now, I'll give you a small example that suppose you have a very large array of planar array or any type of element. So then you have to, if it is useful for generating a beam, then we have to find, we can even identify the measurement technique which can be used as a diagnostic tool, which can help us to even useful for your designing your antenna. So depending upon the type of antenna, one can see that here, same antenna which is having a planar antenna, this is the amplitude distribution. Now, unless until we know the amplitude distribution, we cannot find out, we cannot be ensured whether whatever far field pattern we are going to get from that will be correct, will be the same as what was predicted. So whether you measure the far field pattern or you measure the amplitude distribution, the more important is what we are measuring, how we are measuring. Then we can, even if we know the far field pattern is this, we cannot find out where the error unless until we know the amplitude distribution. So amplitude distribution or the phase distribution, there are different techniques how to measure the amplitude and the phase distribution on the aperture of the antenna that can help us in the diagnosis and evaluation of the performance of the antenna. Now, Microwave measurement can be carried out by both by signal measurement where you use a spectrum analyzer and power meters, and then we can do a network measurements by using a vector network analyzers, scalar network analyzers, and they can be done in three different domains. One is the time domain, frequency domain, and modulation domain, and they are all interrelated to each other. In the frequency domain, when we are working amplitude versus frequency, where we have a spectrum analyzer. When we do time domain, we do amplitude versus time. We have oscilloscope, and when we are doing modulation domain, where we are saying frequency versus time. So, depending on this is what we do in signal measurement, and then when we go to the network, we again use the network analyzer to again measure the S parameter of a device or S parameter of the total antenna system. Now, when we talk about network analyzer, we again have two types of. One is scalar, where we don't worry about the phase, we don't worry about the, we only take the magnitude, the amplitude. And when we talk about vector network analyzer, we measure both magnitude and the phase of the parameter. Now, in the case of antennas, we generally do the vector network analyzer measurement because we need to know the amplitude and phase, because even when a coherent beam is generated from a parabolic reflector, the phase is the only thing which gives the coherence of the beam. And when we are talking about, as I was yesterday, I was saying the shaped beam antenna, the amplitude and phase become more important. Now, these are the few slides I have taken from the manuals of this vector network analyzer, where they have given the difference between the network analyzer and the spectrum analyzer. The spectrum analyzer, whether the single amplitude characteristics, whether what type of side bands are there or harmonics are available in the, because in the case of your active devices, there may be harmonics or second or third harmonics may be sitting there, and one can demodulate and the complex signals, and basically in both the cases we have a tuned receiver inside that, whether it is a spectrum analyzer or a network analyzer. We need to have a detector or a receiver. Receivers, because receivers are generally more sensitive, one can design the receiver in such a way that it has a more broadband and more dynamic ranges available. Now, there can be different parameters H, Y, and Z, but they only more simply we can measure only the S parameter are the only one which can be measured directly from the device. X, Y, and Z, we know that they can be linked with the S parameter, but they are hard to measure because they are mostly dependent on the voltage and current. And even if you put a probe on or your detector at any micro device, its own inductance and its own capacitance will affect the performance. So generally the S parameter is the only way where we can measure the gain, loss, and reflection coefficient of a device. So this is just to give you that why we need to do amplitude and phase, because the linear and non-linear behaviors are there, because non-linear means your amplitude and there may be output frequency may go for a frequency shift, like the mixers. Mixers have undergo the frequency shift, and additional frequencies are created there, because of which this non-linear behavior comes to the picture, and that non-linear behavior can be measured only with the vector network analyzer. Now here I given a very magnitude variation with the frequency. When you have a FT signal and then you give to linear, you get only amplitude variation, but when you give to a non-linear, the frequency also shifts. Frequency means that phase also gets changed. So this is what is shown by frequency. You see the first here, in this case the magnitude only changes, and here in case the frequency also, the phase changes, so that's why you get number of frequency are getting changed. So now in the nonlinear network we have a saturation or crossover or intermodal, another nonlinear effect can cause signal distortion, and that is to be measured. So that's why I'm trying to tell you that why we have to need to measure the phase and why we need to see this amplitude and phase together. So only the magnitude and phase only is required to fully characterize any linear network. and that ensure the distortion-free transmission design efficient matching network, because whether our design is efficient in terms of matching network or with distortion-free transmission is there or not. And when we talk about satellite communication, another parameter comes as group delay. That also we have to see whether how much group delay is there. So everywhere we are talking about phase information or the change in frequency, that means it's a non-linear or a vector error correction we have to do. So for any measurement setup, even if you have any type of measurement setup, the measurement setup itself is having many errors. You have to first calibrate that your measurement setup, then only one can ensure that what measurement you are doing is having a minimum uncertainty in the measurements. Otherwise, uncertainty in the measurements will be very large. And high level of accuracy can be done when we do the vector error correction in the system itself, where when we will calibrate the response of the. So this is what I thought I'll give you all. I am sure you are doing this VSLR measurement. I saw in your labs that VSLR plotted line. They are taking amplitude and phase the maxima and minima. Similarly, here in this case, you take the ratio of the reflected and the incident ray. You basically take that and you get the S1 parameters. And similarly, for the transmission, you take the transmitted divided by the incident reflection coefficient, and that gives you loss or the gain of the component this parameter. And for S parameter measurement, any network analyzer is having basically two direction couplers attached back to back. You must have seen. Now that gives you the property of both forward and reverse. All S parameters, 4 parameters can be extracted for a 2-port device. Now, in this case, what we assume is that all the ports are matched. Then only we measure the S parameters of any individual unit and any individual port. And that if that is not ensured, that there is a reason for having a inaccurate measurements. And another thing is the directivity of the direction coupler is a very important parameter which ensures that the two ports where you are measuring the reflected and the incident signals, they are isolated to each other. So generally we say nearly 30 to 35 dB directivity is required for a direction coupler to ensure that we get a very good accurate measurement of the order of 0.1 dB measurement of the reflection coefficient. So if that is not ensured, then there is a chances that we will get a erroneous measurement. Now in terms of so this is basically as if you see configure your detectors, and these are two back-to-back direction couplers, and then you have incident ray, and here you have DOT, you have a source, and you put a tune receivers or detectors here, and then you can get the ratio of. This is a basic generalized network analyzer block diagram. And if you see a network analyzer, again, if you go for a multi-port, not more than one port, more than 2 ports, then it simply multiply the chain. So the directivity as I indicated here is the only thing which we have to see, that it controls the accuracy of the measurement in this case. But when we talk about so many ports, the crosstalk between each channel also affect the performance. If there is any crosstalk is there, or any port is mismatched even of the receiver at this point, then also even at this point, if you have a crosstalk or a mismatch, then it is going to give you an error of the error measurement, in the measurement error. Then you have 2-port VNA, 4-port VNA, and then different types of this thing. But the only basic thing, this is how it looks, and you have a source inside and a signal separation, where because the source has to be the same, even if when we are measuring a 4-port device or a 6-port device, the amplitude and the phase information of the source has to be same at each port. Otherwise, we are going to have the different reference signals will be coming from the because in all our measurement we are always talking about reference A by R or D by R. So here just to tell the VNA, we have different types of your receiver, or either it can be a tuned receiver or can be diode. And tuned receivers are basically measure the both magnitude and phase, and the detector measure only the envelope of the modulation, and so it gives only the amplitude measurement, and no phase information is available. But in the case of tuned receiver, you have digital signal processing, and then you get a very large broadband behavior. Okay, now I'll go directly to this is probably you must have seen, some of you. Now I'll go to the error model. What happens here is the systematic errors occur. Some are due to the imperfection in the test setup and analyzer, and which can be characterized and mathematically removed during the measurement time, if it is systematic error. But if the errors are like you can just give you an example that if there can be a nearby fluorescent lights or nearby instruments and computers. Even we have seen that this Wi-Fi system which people are using also affects. Suppose you are doing a development of the same band. Generally these are at F band. If you are doing a development and you are doing the measurement many times. Once we had this problem and we spent nearly 1 week to identify the problem. It used to be intermediate problem. Whenever somebody was switching on the Wi-Fi system in the next building, we were getting erroneous response of our low noise amplifier. So that it took for us to find out from nearly 8 to 10 days, then we could correlate that we had a AMI-AMC problem, and because of these cables were picking, these cables which are connected here to the DUT device are picking up the signal at S band, and that level of because of the mismatch here. You see any mismatch, if it is not properly shielded, it can act like an antenna, and any mismatch either it will radiate in space or it will send the signal in the DUT itself. So if there is any EMI, your shielding is not proper, or you have a leakages, you are going to have this wire also can act like a antenna. So this will either receive also signal and it will transmit also. So the error models where we have random errors or the drift errors can be with time, or drift errors can be due to the instruments where they can be removed after calibrations. So one has to do the calibration of a system where either you can remove the noise or switch repeatability and connector repeatability. And how it is done, I'll just say, this is what I was telling you, the crosstalk but inside the S parameter, the source mismatch reflection, the load mismatch reflection, the frequency dependence of the signal of A and R, and the transmission tracking also for the same. So there are nearly 12 terms which have to be corrected before you start the measurement of any device, even for a simple the reflection coefficient measurement or the transmission loss measurement. You have to remove those 12 errors from those device, even that sophisticated device called VNA. Then only one can ensure that the measurement which you are carrying out is what you require, what you need. So this is what you have to make the model of your two-port VNA, and you have to remove each error, and then once you remove the error, then your S11 and S11M, which is measured and which is actually the of the device, will be the same. So just to give you, this is what we had one measurement with data before the correction and after the reflection. You see, you get a very good response. You always worry whether you want to validate your design of your CAD, the analytical tool, and once you do the measurement, you are finding so many errors are there, and that error is not because of your design, that error is because you have not done your measurement properly. So after the correction, your data becomes more smooth, and before the correction was not there, it was giving lot of, as if you are having a multiple resonant frequencies in the same antenna. So there are different ways of carrying out the vector error correction technique. I will not go into the details of that, but I will just try to tell you that it depends on whether if you want to do a one port calibration, then you need to do only 3 systematic error terms we have to measure and they have to remove. And if you have to get a full 2 port, then you have to remove the 12 measurements are required for carrying out and there are different kits are available to remove these errors. And these errors, once it is removed, I will not go into detail, but this is all one can do to remove the error of the total system. Now let us talk about the antenna measurements. Now antenna measurement will be, now once we have, this is what we discussed was a closed structure where we wanted to measure the S parameter of the device. Now when we do the antenna measurement, it can be done either in planar, cylindrical or spherical scanning techniques can be used, which is nothing but near field measurements, or one can do in the far field where you have to generate, basically if you see any antenna, the antenna pattern looks like this. You have a 3-dimensional pattern and it has a coordinate system in which are used for antenna measurements are theta and phi. And you get a 3-dimensional pattern and knowledge of each and every angle, the knowledge of side lobe is very important. You know why? Because you want to find out how much noise this antenna is picking up. You have to integrate the power in all the 3 dimension and then you have to multiply the noise which is generated by the different sources in the space. And once you integrate that, then you get the antenna noise temperature. The antenna also has a noise temperature. Antenna, irrespective of its, even if you make 0 side lobes, then also it picks up the noise from the space because of the back lobe. So depending upon the distance, the antenna generally gives reactive near field in a very close region. If you have antenna and lambda by 2 pi distance, if you go, it gives a very reactive near field. And when you go to lambda by 2 pi to 2d square by lambda, you get a radiating near field. And so in the region, in the near field region, the surface currents are very much prominent, and the surface currents are not, they are more of reactive stored energy, which can be inductive or capacitive depending on the type of antenna. And then once it goes from lambda by pi to nearly 2 lambda or 5 lambda or 10 lambda, then you start getting the radiating near fields. So this is the region where we try to probe and see what type of radiating near fields are. Then comes the radiating far field, which is like 2d square by lambda, which is a place from where you start getting a coherent beam of a far field. Now, ideally speaking, one should always, if you want to do the far field measurement of any antenna, you should have to go beyond 2d square by lambda. That means you imagine now if you are having a 1 meter antenna and your lambda is very small, like Ke band, you need in kilometers this region, your distance between the two antennas to characterize the antenna. Now, what happens when you go to, now what is actually this distance criteria in open range? What is this distance? This is the distance between the source antenna and the transmitting device under test. Distance between the two antennas. Now, if this R is not even if it is 2d square by lambda, then also you see the errors which are there in the here. The errors are of the order of you cannot measure accurately even the first side lobe, and all this other side lobe also there may be some null filling is there, and side lobes are going high. And when you take R into infinity, then you start getting very sharp nulls, and you think otherwise if you are measuring your antenna performance in a close vicinity, then you will be thinking that you are measuring your antenna is not performing well, but because of the coupling between both source and transmit, a different quadratic phase occurs, and because of that you get a very sharp, instead of getting a sharp null, you start getting and null get filled up.